Okay, good afternoon, everybody. I hope you enjoyed your spring break. I did mine. It was too short. So let me start with basically summary of suggestions that you had. I got feedback. I appreciate your feedback. I tried to summarize it here, and basically this is the summary of the points which were repeated more than once. Okay, so and I sorted them based on the frequency. So as you expect, the first one is the exam time was too short, and I agree. Okay, so for the second one, we try to adjust that. You are interested in more examples. TA and I are working together to give you guys more example on the second part of the course for confidence interval and hypothesis testing and what we learned so far. And hopefully the next would be for ANOVA and regression. ANOVA and regression should be covered before project due date, and I agree. And what we are going to do, I think hopefully either this class or the next one, we finish ANOVA and we start regression, and by 1 or a couple of weeks we are going to finish regression. So you have enough time, because I know that these two tools are very popular and very commonly used in data analysis, okay? Both ANOVA and regression. So you learn these two before start working on your projects. By the way, the project abstract is due what? Friday. Okay. So you wanted partial grading. Hopefully we can do that for the homework, and especially for the second exam as well. Timely grading, I agree. I have your homework 3 here. And hopefully for the second exam we can give you the result back sooner. Post solutions of examples on the slides. So that one, I prefer, this is kind of like a personal thing, I prefer not to do that because I want students to come to class. Okay? If you have everything, then you don't come to class. So that's one of the reasons I don't do. But if you, for some reasons, if you miss that one, so you can send me an email, okay, I missed the class, I don't have this basically example solution, can you help me? I try to basically provide that solution and send it to you. Let the student access the videos. This is also one thing on case-by-case basis. I can do that. For example, if you miss one class for a well-justified reason, I can ask distance learning student to give you a temporary access to the videos. Okay, but not for all classes again. Yeah, that was the. Anything you want to add? Anything that you want to discuss? Any other suggestions or any more comments? Anything? Good? Okay. Good. So let me switch to the analysis of variances slides. If you remember, so if we have more than one population and we want to test the hypothesis that the means of these populations are the same or not, then we use analysis of variance. Okay, whether mu1 is equal to mu2 or mu3 or mu4, all these are equal or not, at least one is different, then we use analysis of variance. And why we call it analysis of variance? Because we have some basically total variation, and we divide this variation in two components. One is between group variations, which means that whether the means of different population are different or not. Okay, so basically that part of variation is because of the difference in the means. And within group variation, which we expect each population has its own variance, so we expect that some variance should be observed within each group or population. And we said that, okay, if we divide the total variation into these two components, then if the contribution of between group variation is very small, then we can say there is no strong evidence of rejecting H null, which means most of variation is because of within group variation. And between group variations is small. That implies that the difference between means are very small. Based on that, basically, this is the decomposition in a mathematics form. We developed a test, okay, which basically we show that under H null, this follows a chi-square distribution, this follows a chi-square distribution, and therefore this also follows a chi-square distribution. And we said, okay, how we can do the test? We can divide the SS of treatment by a scaled version of SS of treatment by SS of error, which gives us the mean square treatment and mean square error. This is going to be our test statistic. We compare the test statistics with a critical value, which is this guy. Then if it is greater than this, the critical value, H null is rejected, and means are not the same. So just to remind you, this is sort of a chi-square distribution divided by degrees of freedom, okay? And another chi-square distribution divided by degrees of freedom. Therefore, we have F distribution under H null. Any questions? Concept clear? How we do that? Okay. And in terms of calculations, what we do, we use these equations to calculate sum of a square total, sum of a square treatment, or also we call it between group variation, and sum of a square error, which is also sum of a square of within group. If we calculate these two, SSE is SST minus SS of treatments. Then we construct a table as this, and based on that we can say whether we reject H null or not. We had one example, we went over that example, and we said, okay, based on the analysis of variance table that you have, can you give me a confidence interval for the mean of each population? We said yes. How we can use, we don't know the variance. What is that noise for? Oh, they are moving something. Yeah. Okay, they're moving something. That's fine. I thought this was because of the microphone, but not. Okay, so since we don't know the variance, we need to estimate the variance. What is the best estimator for variance? Is mean square error, okay? Because mean square error, which is SS of error divided by degrees of freedom, okay? That is the best estimator, like a unbiased estimator for sum of a square. And as I said, for two population, MSE is the same as what? For two population, MSE is the same as pooled estimator. Okay? Then we have this T distribution, and this is the lower bound and upper bound. Okay? As one example, what if we want to do basically confidence interval for the difference of two population means? These are the equations that we use. And as you can see, the variance is doubled because the variance of each population, we assume they are the same. If I go back very quickly to the main assumptions of ANOVA, too much. That's one of the most important assumptions. Population or factors have equal variances. Okay? Therefore, the variance for the difference is the summation of the variances. And since they are the same, so it's 2 times MSE. Okay? So why this is important? If I want to see whether two specific populations, let's say we have N populations, A populations, whether two specific populations have the same mean or not, I can construct this confidence interval. If 0 belongs to this confidence interval, they are the same, otherwise they are not the same. Okay? These are basically after ANOVA analysis. When you do analysis of ANOVA, if they are rejected, then you can basically do some more analysis in terms of saying, okay, I know that H null is not true, which means that otherwise. This stands for otherwise. This, if H null is not true, at least one mu is different from others. Okay, that's up to here is ANOVA. But the question is which mu is different from others. Okay, you can either answer it by basic confidence interval or something else which is called a least significant difference. This is also kind of like a hypothesis testing to see which means are different from others. Okay, so what we do basically a paired comparison. In that example, we had, let's say, 4 populations. So for choose 2, how many combinations do we have? 6. Okay. And what we do, we calculate that LSD. Okay. This is sort of like a threshold. What capital N is total number of experiment that we have, and basically when this is for the case that N is fixed, so which means that for each population I have the same sample size, or replication is fixed across different populations, and this is for the case that each population has its own sample size. Okay, and the capital N is the total number of experiments. Then I calculate, let's say I want to compare or I want to test whether mu I is the same as mu j or not. Then what I do, I'll calculate mu y bar I dot and y bar j dot and compare it with that LSD. If it's greater than that, greater than LSD, then there is a significant difference. Otherwise, not. Any questions? Is it clear? Okay. Here is the same example. Just to refresh your memory, that's the example that we have. We have different, basically, hardwood concentration. So 5, 10, 15, and 20. And we have different, basically, we want to see if the hardwood concentration would affect the strength, tensile strength. We performed ANOVA. It was rejected now. Was it rejected? I think so. Based on the ANOVA table that we had. Now we want to see which two are different, which two populations are different, or which two levels of basically hardwood concentrations are different. So what we do, this is the average sample average for each population. Okay, for 5% is this guy, for 10 to 15% is this guy, for 20% is this guy. Okay, so based on this, you would basically guess that probably these two are not different, but all other combinations are different. All right? So let's see how we can solve it using LSD. So let me start with four versus 1. So what I need to do, y bar 4 dot minus y bar 1 dot, and which is 21.17 minus 10, and this is 11.17. Then 4 versus 2 would be 20.117 minus 15.67. That difference is 5.5. Third one, 4 versus 3, is the same thing, minus 17, which is 4.17. 3 versus 1, 17 minus 10, which is 7.00. 2 versus 1, 3 versus 2, sorry. Then this guys is 17 minus 15.67, which is 1.33. And the last one is 2 versus 1, which is 15.67 minus 10, 5.67. Okay, so what is the threshold? Threshold is LST. In this case, LST would be T of, let's say alpha is 0.05, T of 0.025, and the degrees of freedom is the degrees of freedom of error. In that case, degrees of freedom is A minus 1 times N, or A times N minus 1. It's the other way around. Sorry. A times N minus 1, which is 4 times 6 minus 1, which is 20. 20 and 2 MSE divided by N. And N is 6. Okay, so mean square error from the ANOVA table is 6.51. So if we calculate at the end of the day, we get 3.07. So 3.07 is the threshold. So this one is greater than 3.07. So this is significant. The same thing here, this is significant. This is significant. This is significant, this is significant, this is not. So I can say 2 and 3 have the same mean, but the rest have different means. Does it make sense? Just be careful when you have basically different sample size, your threshold is not going to be fixed. It depends on the sample size of these two populations that you are comparing with. Okay? Any questions? Is it clear? Okay. Let me see. So, model adequacy checking. Basically, this is sort of like how we can validate the assumptions that we have. Do you remember the assumptions? One is what? Let me see who remembers that. You already have this slide, so probably you can tell from there. But the first one is residual, like the epsilons, which was like random error, is normally distributed. Okay? And they are independent. That's basically the first assumption. The second one is summation of tau I is equal to 0. And the third one is basically populations factor have equal variances. So this one is automatically valid as long as we assume that this is not a random selection of populations. Okay? But 1 and 3 we should check. We should check whether they are kind of like random, whether they are normal, and whether the variances across different populations are the same. Okay, how we can do that? So you remember that was basically the main statistical model that we had. Okay, and all assumptions are based on that epsilon ij, because epsilon ij normality depends on that, independency depends on that, and the variance also depends on epsilon ij, because we are talking about across different populations. And populations index is what? J here. I'm sorry, I here. Okay? So what I can do, I can estimate that random error and then check these assumptions using that estimation. Okay? So I'm going to estimate that random error and call it residual. So EIJ is an estimate of this random error. How? It's easy. I can basically estimate Yij. So put it this way. So your Yij is mu I plus epsilon ij. Okay? So what is the estimation, good estimator for mu I? Is the sample average of that population. Okay? So what is the sample average of that population? Is yi dot. Okay? So y bar I dot. Actually, I think there is a typo over there. This should not be y bar ij. It should be y bar I dot. Let me fix it right away. Okay? So if I subtract Yij, y bar I dot from Yij, then I get an estimate for epsilon ij. And I call this guy residual, Eij. This is residual. Does it make sense? Very simple. Is it clear? Any questions? Again, this is the model that I have. I want to estimate this guy. These are the observations that I already know. Okay? This one should be estimated. This is the mean of each population. So what is the best estimator for the mean of each population? Sample average. Subtract the sample average, then you get estimate for epsilon ij. We call this residual. Okay? For this example, as you can see, the residual are here. Okay? For each observation, I have one residual. So I can use this to check whether it's normally distributed or not. Let's start with normality test. So there are three methods for normality test. One is normal plot, histogram, and goodness of fit. Okay? So normal plot is a visualization tool. I haven't talked about this yet. I'll talk about that later. But if I'll teach you how to use Minitab for normal plot. Basically, you have normal scores here and residual value here, and if they are scattered around basically a straight line, you can assume it's coming from a normal distribution. Okay? Just for now, you need to basically know how to interpret that. Okay? How to construct that, I will teach you later after I'm done with regression. Okay? Is it clear? So if you have a normal plot, if they are scattered around like a straight line, we can say observations are normal. Histogram, you already know how to do, to basically plot a histogram. If it is kind of like symmetric, then they're coming from a normal distribution. But the best way for testing that is a goodness of fit test. Again, I'm going to cover this after regression. Okay? So these are the three basically methods for saying whether the residuals are normal or not. Second one is the variance consistency. Okay? For the variance consistency, what we can do, we usually plot the residual value versus the y bar I dot. Okay? And also the residual values versus the level of factors that we have for the first population, second population, third, and fourth. If the variance is consistent, so actually we have residuals, okay? For the first 5%, these are the residuals value. How many observations do we have? 6. As you can see, these are 6 numbers. Okay? So the variance is related to what? To the length of this line. Okay? If the variance is larger, so this line should be longer. Because this is the minimum residual, this is maximum residual. Okay? You remember? That was our assumption. Epsilon ij follows a normal distribution with this mean and this sigma squared. Okay? So, The longer the line is, more variance you have. If you plot it for basically different populations, and if they are almost in one bound, then you can argue and say, okay, there is no, but the variance is constant across different populations. But if you see some funneling behavior, for example, something like this, then it shows that when population changes, the variance decreases in this case. Okay? So in this case, you cannot use ANOVA. Okay? This case is fine. Over there, I would say it's fine. It's a little bit tricky to say in terms of just plot. If you take a course called Design of Experiment, you will learn a test which is for testing whether the variances are the same or not. You can basically do this test to see if the variances are it. This is called Bartlett test. But anyways, for this course, we just use the visualization. Okay? And it's not for sure, but it gives you some ideas. If you see something like this, definitely ANOVA cannot be used. That one should be okay. Okay? The same story for residual values versus Y bar. Okay? Any questions? Anybody can tell me how I can check the independency? Because this is normality we know. This is variance consistency. How about independency? That's the third assumption that we have. How about in reality? Any guesses? We need to use residuals, by the way. That's a hint. Nope. Okay. So what you do, you plot residuals versus order of experiment or order of data collection. Okay? You remember I told you need to do randomization? So basically the order of observations that you see, where is that table? Here. So this is not necessarily the first experiment. It could be the 10th experiment. So you have an order of experiment. Okay? So you plot the residual versus order of data collection or experiments. Then if there is no non-random pattern, if everything is random, then you say they are independent. Otherwise, the dependency assumption is not valid. Independency assumption is not valid. For example, if you plot and they are something like this, that's fine. But if you plot and it shows you something like this, then there is something wrong with your randomization probably. Or your randomization, there is a factor that even you randomize your experiment is affecting your basically data collection procedure and experiment. In that case, could be some seasonal factor. Okay? Or if you see something like this, just going up or just going down. Any non-random pattern. So what I mean by non-random, you can use the information of previous point to estimate the location of next point. Okay? So if I see these data points, I can say probably the next one would be here. This one, I'm not sure. This is random because I cannot guess the location of the next one. Any questions? Are we good? Okay. Yes, that was the last one. So sure, yes. So two-way ANOVA. So what if we have more than one factor? Okay, so far we had one factor, which was in that example was basically hardwood concentration, and we want to see if hardwood concentration would affect our response or not. So in some cases, we have more than one factor. Okay, for more than one factor, we have two cases. One is blocking or randomized complete block design, and the other one is basically two-way ANOVA with interactions. I start with the blocking, and I'll tell you what I mean by blocking. In some examples, when you do the experiment, the experiment conditions are not homogeneous. Okay? Let me give you one example. Let's say we have different washing solutions, and we want to compare whether these solutions are performing equally or not. So what we do with different basically we use different solutions and try to run the experiment. Okay? But the way that we run the experiment, because of the constraint that we have, we cannot do all the experiments in one day. Okay? So we do the experiments in 4 days. Okay? So all the experiments that we have, and these are the response variables. So what is the problem? We are not sure whether the condition of experiment in day 1 and day 2 and day 3 and day 4 are the same. Okay? If they were the same, then we would have simple one-factor ANOVA. And we consider that 4 as what? We would consider that 4 as replications. Okay? You remember, for regular ANOVA, we had different levels of factor, like 5% hardwood concentration, 10, 15, and 20. And we had replications here. Okay? Here, I cannot say these are replications. Why? Because the condition of experiment in day 1 could be different from day 2. If they were not different, I would consider it as replication. And I use one-way ANOVA. Okay? So if you have a factor which basically changes the homogeneity of the experiment, then you need to use blocking or two-way ANOVA. Okay? So what blocking does, it tries to remove the effect of days or that block factor from the experiment, and then give you a correct assessment of the factor that you want to analyze. Okay? Again, question of interest here is, do these solutions have the same efficacy? Okay? Have the same mean or not? Factor of interest is type of solution. What is the blocking factor? As I said, blocking factor is the one that changes the homogeneity. Here in this case is day. Why? Because day 1 and day 2 could be different. And that's the definition of block factor. It's a nuisance factor that affects basically the homogeneity of the study. For example, lab conditions could be different in days 1 to 4. Again, the question of interest is the same. Whether mu1, mu2, and mu3 are the same or not, that's exactly the same thing. Just the problem setting has changed. Okay? Any questions? Is it clear so far? What is the difference between one-way ANOVA and two-way ANOVA? Yep.
Does it matter if the block factor and the factor of interest are switched?
So the question is, does it matter if the block factor and the factor of interest switch? Actually, it does matter. Okay? In terms of calculation, no. Okay? Because you do the calculation the same. But in terms of performing the hypothesis test, yes, it does. You will see in a minute. Because we do the hypothesis testing not on block factor, on the factor of interest. Okay? Yes, and actually the way that you define it should be based on the setting of the problem. So I don't care about days. What I care is whether the basically the efficacy of those solutions are the same or not. But day is a nuisance factor. I cannot do anything about that. Why? Because I cannot complete the experiment in 1 day. I have to extend it to 4 days. Therefore, I'm creating a new factor which is a nuisance factor. Okay?
The block factor can be dependent on the factor of interest?
No, actually, if it is dependent, then there is basically a second type of two-way ANOVA. So in that case, this is not going to be nuisance factor. This is a separate factor, and you need to basically find not only the effect of basically type of solution, but also the day as well as their interactions. That's what you said. That's the interaction. Level of day depends on the level of solution. Yeah. That's the second type of two-way ANOVA. Yes.
Blocking factors, and is there like a multi-way ANOVA kind of thing?
What factor?
Like multiple blocking factors?
Oh, yes. Can we have multiple blocking factors? Yes, we can, but not in this course. Yeah, in reality, we can. In the ANOVA experiment course, as I said, you will learn what if you have more than 1, 2, or 3, or 4. It goes up. It's called Latin square, hyper Latin square, and they have different names for that. Yeah. But for now, we just limit ourselves to one, basically, block factor. Any questions? Good? Okay. So the problem setting is very similar in the sense that we have very similar, let's call it design table. Okay? These are the observations. Instead of replications, we have block. So how we can treat basically the block, we can treat them as replication as well and do the same calculation. So these are the different treatments for one factor, and these are different blocks. Let's say we have A populations and B blocks. And these are the experiments that we have. Again, the same notation, row summation, we show it by yi dot, and basically column summation with y dot j. Okay? And this is basically total summation. And we also calculate row average and column averages. And this guy is what? Total or grand average. So what is the model? The model changes here. You remember previously model was this guy, which I wrote as mu plus tau I plus epsilon ij. So this was overall mu, the effect of each population, and random noise. Okay? Here we have one more basically component, is overall mu, the effect of each factor, and effect of each block. Okay? Plus epsilon ij. That's yij. Okay, now you tell me. What happens if I have a block experiment, type of experiment, and I use one-way ANOVA? What is the problem with that? Yes, but how it would affect my calculations? Look at the models.
It adds an extra bit of variance to your...
Exactly. So this guy, so compare the block model and this guy. Okay? So what you get here is tau I, and this is epsilon ij. This is epsilon tilde ij. So you are combining the effect of your block with your noises. Okay? So if you combine the effect of block with your noises, what's happening? The variation of noises going to be bigger. And the possibility of rejecting H null gets smaller. So basically, even if you have significant tau, that could be masked by significant beta j, if we combine them. Again, if beta j exists, and I basically use one-way ANOVA model. So what I'm doing, I'm combining the effect of block with the effect of random noise. That inflates the within population variance. Okay? When within population variance inflates, your F0 decreases. Therefore, with high possibility or high likelihood, you do not reject H null, which means tau i's are not significant. Okay? That's what happens. So we need to basically decouple them. Okay, let me be fast a little bit here. Any questions? Is it clear what happens? Is it? Or we are busy with our cell phones?
Plot, let's say, that isn't random is a two-way ANOVA, kind of your next step, and you're looking to estimate.
That's a good point. If you can find that factor that caused this non-randomness, then you can separate that. Yes, exactly. Yes. Okay. So how we can calculate? Again, total variation. Now we decompose it into three levels, three components: SS of treatment, SS of block, and SS of error. And here are the equations for each of them. Okay. This is SS of treatment, SS of block, and SS of error. So these are the equations for that, like simplified equation. They are exactly the same, but this is kind of like simpler to calculate. So what you do first, you calculate SS of total using this equation, then treatment, then blocks. If you have these two, you subtract it from total and you get error. That's it. Okay? So the difference between this one and one-way ANOVA, in one-way ANOVA we didn't have SS blocks. Then what you do, you calculate mean square. So mean square of blocks, mean square of treatment, and mean square of error. Each one divided by degrees of freedom. Degrees of freedom for treatment is A minus 1, which is the level of factors or number of populations minus 1. The second one is B minus 1, the number of blocks minus 1. And the third one, which is MSE, is A minus 1 times B minus 1. Can you see the difference? The degrees of freedom, A times N minus 1. Here is A minus 1, B minus 1. Any questions? Okay. Then we calculate F naught, which is MS treatment divided by MS error, and then we compare it with the basically the threshold or critical value with these 2 degrees of freedom. Okay. So again, we have the table, ANOVA table, and we calculate F0. If it's greater than the threshold, we reject it. Let me continue with one example, or maybe you can work on that example. Because, yeah. Let me see. Maybe not. Let me finish this one, maybe, and then next class you can work on the other one. So the question is about fabric strength. An experiment was performed to determine the effect of 4 different chemicals on the strength of a fabric. These chemicals are used as a part of the permanent press finishing process. 5 fabric samples were selected, and an RCBD, randomized completely block design, was run by testing each chemical type, and the data are shown here. So as you can see, the main goal is to see whether chemical types are the same or not. However, we are trying on different fabrics. So these fabrics could be different. So this is our block design. In the exam, it's very important. I give you problem statement. You need to figure out which one is factor of interest, which one is the nuisance factor or block factor. Okay, in this case, completely makes sense because we want to test this guy. Therefore, the other one is fabric sample. Okay. The fabric sample is basically our block. So we need to find the components and of basically the ANOVA table. So for ANOVA table, we have sources of variation. SOV stands for sources of variation. One is treatment. The other one is block. What else? Error and total. So what is sum of a square? Okay, I need to find SS of treatment here, SS of block here, SS of error here, and SS total here. Then degrees of freedom, MS, which is SS divided by degrees of freedom, and finally F naught. Okay, so we should start with SS of total. So equations are given right here, as you can see. So it says each variable squared and then add them up. 4 squared minus y dot dot, which is 39.2 squared divided by a times b. What is a? A is what? 4 and b is 5. So 4 times 5. Okay? And if you calculate this, this number would be 25.69. How about SS of treatment? Maybe you cannot see it here. Write it down. Up there. SS of treatment, the equations are there. So we are 1 over b, which is 1 over 5 times summation of y I dot squared, which is 5.7 squared up to 17.8 squared, minus y dot dot 39.2 squared times 5 times 4. This gives me this number, 18.04. And SS of block, I do the same thing, 1 over a, which is 4. Now I work with 9.2 squared plus all the way 7.6 squared. And minus 5 times 4. And this is basically 6.69. So SS of error is SS of total minus SS of B minus SS of treatment. In that case is 25.69 minus 6.69 minus 18.04, which is 0.096. So from this you can guess, okay, that should be pretty significant compared to this guy. And see, but let's complete the ANOVA table. So I have SS of treatment, which is 18.04, SS of block, which is 6.69, SS of error 0.96, and total is 25.69. So what is degrees of freedom? For the first one is a minus 1, which is 3. Second one, b minus 1, which is 4. Third one, a minus 1, times b minus 1, which is 12. We need to find mean square divided by 3. .01. The other one is 6.69 divided by 4, which is 1.67. And MSE is 0.96 divided by 12, which is 0.079. So what is F0? This guy divided by this guy. So your F naught would be 0.1 divided by 0.79, which gives you 75.89. Then you compare it with what? With F of alpha, A minus 1, and A minus 1, B minus 1. In this case would be F of 0.05, 3, and 12 degrees of freedom. And your F0 is greater than this. If you look at the table, definitely is greater than this. Therefore, reject H null. There is a difference among solutions. Okay? Any questions?
A minus 1, B minus 1.
Oh, yeah, yes. Thank you. Thank you. So we continue on basically Wednesday. Just one quick point. Sometimes you can also calculate F for block. What does it tell you? Think about that. When you calculate F for block, what does it tell you? I will answer that question on Wednesday.